My name is Graham Johnson. I work at IBM on IBM's Java virtual machine. I may refer to it a few times as J9. And today we're going to be talking about JVM support that we've been working on for about the last 18 months for building multi-tenant applications in Java. We always get to start with the legal disclaimer. What you're about to hear is a forward-looking talk, so any of the dates you see mentioned, not carved in stone, but the talk is accurate based on our best knowledge today. This is me, pre-goatee. I've been building virtual machines for basically my entire professional career. I started with a language called Smalltalk back in the early 90s, and after building VMs for other languages like PHP and working on portability and a lot of the debug and JIT support, my new day job is making the JVM a better citizen in cloud environments. That includes things like the multi-tenancy support that we're going to be talking about today, and improving elasticity, increasing the number of artifacts that we can share between JVM instances, and the classic good VM stuff of footprint and performance. What you should walk away with is good understanding of what multi-tenancy is, what it's good for, why I think it's compelling, some of the challenges about building multi-tenant Java applications today, and hopefully get a good grasp at some of the features that we're working on today that we think it's going to make it easier to convert existing applications into multi-tenant deployments. Basically allow you to stack more applications on the same piece of hardware than you can today. So here's the plan for the next hour. We're going to level set, hopefully get everybody a baseline about what multi-tenancy is and what it's all about, learn about some of those challenges. We're going to spend a fair amount of time talking about dealing with bad behavior. So it's one thing to get a multi-tenant application working. It's another thing to keep it that way. That requires good walls between your tenants. We're also going to explore where the limits of density are today. I've got a few performance numbers that are fresh in the lab. It's a stake in the ground. Things are going to change pretty rapidly over the next year, but this should give you a pretty good peek at what we've got. As I say, we've been working on this for about 18 months with a combined team of VM guys, class library guys, and JIT folks. So we've got a pretty good comprehensive solution, I think. So the basic premise: simplifying the software stack by removing all the extraneous bits makes things simpler. When you remove stuff, footprint goes down, complexity tends to go down as well. So the simpler we can make it, the cheaper it is to run and deploy. And my favorite anecdote here is actually comes from my living room, where we started off with the classic 5 remotes, and my first pass at Simplification, which I thought was great, was the intergalactic remote on the left from Logitech. I enjoyed the power that it gave me. My wife, my grandparents, and the kids did not enjoy that level of control. And from an operational perspective, it required lots of me time to actually have the audio, video, visual stuff working on a reliable basis. So to get beyond this, I had to kind of reevaluate what I thought was extraneous and what wasn't extraneous. That led us to iteration number 2, which is a little Apple TV on the remote on the right-hand side. Honestly, I didn't think it would work. Get the little pad, 2 buttons. It seems like you've gone a step too far. You're giving up a fair amount of power there, right? The increase in customer satisfaction, as soon as I toss the other one, instant. Everybody's happy. Simpler, it's predictable. It's actually cheaper to produce, which is important when your 4-year-old goes and dumps the remote and a cup of coffee. It's $20 to get a new one instead of not $20. Requires a bit of hard engineering work on my part, right? Had to refactor some of the home media stuff around the house. I view that as an operational thing. Biggest thing was probably a shift in mindset on my side to think about what was extraneous and what really mattered. So let's see if we can take that it just works approach into the data center. Second example, if you're a pragmatic programmer fan, you hear about single source of truth, and make sure that there's basically one piece of machinery in your code that does a given job. Right? So if you have a bug, go one place, fix it. Seems obvious, but for most of the new grads that we get in, first we have to talk them down off of the complexity sort of wall that, the more buttons and knobs that I can add to a solution, the better, because I enjoy doing that. And you hand this to an ops guy, and they don't appreciate your buttons and knobs. The second biggest thing that we have to teach new programmers is actually copy and paste isn't reuse, right? You're just picking up code, duplicating it all over your code base, turns into a maintenance nightmare. Although it's really, really easy, right? Seems fast, seems expedient. So this one hit home for me because I've seen the problems that it can solve, and I fight with this day to day. But then I look down the hall into our labs, and we suffer badly from the copy and paste problem. We literally have an army of clones sitting in the lab that we manage individually. And the techniques that you use in your data center, when you've got 20 machines, don't really scale that well to 200 or 2,000. So again, simplicity, reducing the number of moving parts, I think can have a big win in some of the big software stacks. So thank you for bearing with me through the anecdotes. Here's how I think simplification and the principle there relates to multi-tenancy. So instead of having multiple copies of operating systems, app servers, your apps deployed into them, a multi-tenant application says, let's have just one. One application, we're going to look at who the request is coming from, figure out which tenant we're talking about, and have one copy of the OS, one copy of the app server to manage, one copy of the app. If you want to be really extreme about it, one copy of the database. Why is this a good thing? Well, you've eliminated a bunch of parts. Parts all cost footprint. But in addition to the footprint, which I as a VM guy appreciate, you've also taken a lot of operational complexity out of the whole story. So now you look around at the industry, and these a lot of the companies here are the examples that you normally see. Salesforce.com is probably the best example I know of a stack that's been built for multi-tenancy from day one. And that's great if you've got the forethought to have done that. Other folks have. Core Metrics is an IBM company. Again, built with multi-tenancy in mind from day one. But for the rest of us that didn't think about tenants 10 years ago, what the heck do we do, right? And that's why I'm calling out companies like Atlassian, right? This one's near and dear to our heart because we use a lot of Atlassian tools in our development shop. These are things that index your CVS repositories and track your bugs, and there's wikis, and they got build engines. And if you'd asked me 5 years ago, is that the kind of tool that you would buy in an as-a-service model? The answer would be, not a chance. But if you look at how they're running their company today, they've got this new Atlassian on demand, and the bulk of their development effort and their sales effort is going into an as-a-service model in a pretty non-traditional way, right? Another example, New Relic. They're an application performance monitoring company. We see a lot of them because we're VM guys. We care about performance. They care about performance. Again, another non-traditional kind of tool where normally you would set up profilers and things like ITCAM, run them behind your firewall, and that's how you determine if your servers and apps were healthy or not. They've turned that on their head. There's a small little emitter that runs inside the JVM. All the heavy lift happens up at New Relic headquarters. And as a user, you're basically paying by the month and deciding how big your monthly bill is going to be, and that controls your service level. So the take home here is there's a lot of existing software out there, and if you're driven, there are opportunities to take that and bend it a little bit and turn it into an as-a-service kind of world. It's not easy. Hard engineering work needs to be done. And I think there are actually some things that the JVM can do to help with this kind of transition. Excuse me, my voice is leaving me. So let's talk about software stacks. There's a giant white paper that accompanies this diagram, and I realize it's probably pretty hard to read. The important thing is that there are a fair number of bubbles on the chart. At the bottom you have hardware, that's the dark box. Operating system is close to it. There on top you have middleware, databases, schemas inside the database, finally your application instance riding at the very top. So that I just described S0. And that's the no sharing story. If I had dedicated hardware for everyone, My deployment of a new tenant, when they knock on the door and says, I'd like to sign up for your service, means I go and acquire hardware, install operating systems, stand up the whole stack. Great isolation. I can customize the heck out of it without hurting anybody else, but it's slow and expensive. Right? S2, or the multi-VM stack, is basically where most people gravitate today. And really, it's a very similar picture. The only thing we've done is added a hypervisor. So now I have multiple operating systems stacked up on a given piece of hardware. Again, traditional isolated database middleware stacks, applications riding at the top. And the good news here is that it's easy, right? All of the tools you know and love today all work here as well. Other piece of good news is you can now capture idle cycles. So if one of those stacks is idle and the other one's busy, you can share some compute resource. The bad news is that you now have neighbors suddenly, and noisy neighbors can cause you problems. So let's keep going. Because each of those bubbles is expensive, right? How big is an operating system? Measure it in gigabytes, right? Every application server instance, also gigabytes. So let's keep trying to merge some of those bubbles. If I look at the S2 or multi-stack picture, the difference here is we now have one operating system. And the challenge is suddenly we've opened ourselves up to resource collisions. So you can meet on the file system, you can meet on ports. There is only one port 8080 on the box. So these are usually problems good ops guys can deal with on their own without too much developer intervention. But you're starting to have to spend money to move from the left-hand side of the slide over to the right. Shared middleware, harder still, because now you're not only sharing an operating system, you're sharing an application server instance as well, so your neighbors are even closer. And today, really, the JVM doesn't give you particularly good walls to protect one application from another. And that's a lot of what we're going to talk about today. As we keep going, so into the S4 stacks and the S5 stacks, you'll notice that that purple box riding at the top that says multi-tenant application, that's merged together. So at this point, your code is actually tenant-aware. And usually your decision point there is whether you have a separate database schema for every tenant, or if you go all the way and have one database schema and add tenant IDs to all of your tables. But again, going from the far left over to the far right, the further to the extreme of sharing you get, the more development effort is required to get there. The other interesting point, though, is removal of bubbles is great, right? The real point is that the customer can't see what's behind the curtain. So they don't care if you're running out to FedEx and getting new hardware and setting it up, as long as you can do it quickly and don't charge them an arm and a leg every month. What the customer does care about is stuff like cost, right? They're going to see the monthly bill at the end of it. And the smaller that is, the happier they tend to be. And if it's low enough, people are willing to take a risk on a service they might not believe in until they try it. Right? That's what a lot of the APM guys are doing. So if it's like New Relic, it's free to try for a while. If you like it, they have you hooked. You're paying a few bucks a month. Time to value is always an interesting challenge because traditional cycles say, let's go through a long sales process. We'll schedule up a project to actually get the gear installed in your heavy labs and the application set up and running. And you're usually measuring the amount of time in months. If you can bring people online quickly and allow them to try, ideally self-serve, I think there's actually some nice results to be had on most companies' bottom lines. Quality of service is another interesting point. Instead of people having to decide how much infrastructure their IT teams are capable of running, they replace that decision with how big a monthly bill am I willing to run and let somebody else deal with setting up the hardware, making it scale, and dealing with power and cooling it. And not all IT teams are created equal. Sometimes there's big backlogs in getting stuff done internally, and oftentimes it's easier just to pay that monthly bill and be up and running in days or weeks rather than months. From the provider viewpoint, these guys that are charging tens or hundreds of dollars per month, the cheaper they can deliver that service, the happier they are. It's money in the bank for them, right? And by eliminating parts, so we took operating system instances out, we took application server instances out. At the extreme end, we had single database tables. When things change in those stacks and you need to go and patch the operating system, it's a lot better to have one than 1,000. Same deal with the app servers, right? And database migration, all that kind of stuff. So although it's scarier in a sense because you have a lot more applications balanced on one point, the number of moving parts goes down, the operational costs, if you're clever, can go down. And let's keep going. So that was the million-mile-an-hour introduction to multi-tenancy. And you may not be ready to go and convert your payroll applications to a world like I described, where you're sharing database tables with your competitor beside you. But for a certain class of application, typically stuff that's put up quickly, maybe isn't going to last for a long time, doesn't have to have 3 or 4 nines of availability, the multi-tenancy story is actually a pretty good fit. So we're basically at base camp. For the next maybe 20 minutes or so, we're going to climb to the top and understand what you need to do to Java and the JVM in order to deliver really good multi-tenancy support. So I alluded to this a bit. The biggest reaction I usually get at the start of this talk is you're trading off isolation, right? I no longer have an operating system to protect me or a process barrier to protect me. I'm suddenly in this big soup with other applications. And the answer there is yes. So is it the right choice for everything? No. But I think on the JVM side, I can reduce the chance of a failure happening. We can already take a program and have it run the same way on hardware ranging from the little Raspberry Pis you saw to the giant mainframes. Don't have to change the code at all. So the VM is doing a lot of magic already to make that happy for you. Asking it to do a little bit more seems reasonable. The impact of failure, however, is your problem. And the way we deal with that today is all about choreography, right? So if you've got a mission-critical service, you probably don't have one app server serving it. You've got a load balancer in the front. You've probably got multiple apps, right? That's choreography. And you're usually careful with your choreography, right? You understand how the machines sit in the lab, so you're going to avoid, say, machine failure. Like there's no point in setting up a stack on the other side of a hypervisor. So if the hardware goes down, the whole thing disappears, right? So you know about the same machine problems, you know about the same rack problems, you know about the same geography problems. It's standard IT stuff that we're all doing today. It becomes even more important for multi-tenancy, though. Second big challenge here, though, is cost of entry. So again, most people are sitting at this sort of multi-VM stack where they use traditional tools in conjunction with a hypervisor. The reason they do that is it's easy. Your neighbors are relatively far away. The hypervisors are actually pretty good at protecting one guest from another. And as soon as we get beyond that and we start sharing operating systems with other guys, we've got sort of these port collision, file system collision, security challenges. But the VM can actually start to help you in these instances, right? So if I'm running 2 or 3 app servers in a given operating system, a lot of the code there is actually identical. And the IBM JVM, for example, has got a feature called shared classes, where we split every class into a RAM half that contains volatile information and a ROM half. The ROM half is the same from VM to VM. Those things can be shared. Dump them in shared memory, and you can recoup somewhere between 60 and 130 megabytes of memory per VM. So that's pretty decent, right? If we keep going and we start merging those middleware bubbles and the database bubbles, we've got a data isolation problem, right? Tenant A is in the same arena as tenant B. We need to do something in order to keep them separate. If tenant B is going to be misbehaved and suck up all the computational resources, we need to erect some walls so that can't happen. And again, I think this is work the JVM is doing today anyway to a degree. Asking it to stretch a little bit and provide some primitives to help here isn't a giant leap. So I'll be a VM guy throwing stones at Java for a slide. When I look at a JVM instance, there are some issues there that aren't great stories compared to some other languages. Java heap is a big problem. It's hundreds of megabytes of memory. Most JVMs today aren't able to share heap objects between JVMs. So it's all private space. It's not amortized in any way. In order to keep that heap clean, you've got garbage collection threads. Typically one of those per core. Depends a little bit on how many cores are in the box. But the GC is stealing time from your application as it's trying to do work in order to keep the heap clean. Just-in-time compiler is another fairly big source of both CPU burn and memory burn. Consumes tens of meg of memory just for the code caches and metadata on its own. The code that we're generating, again, private, it's big. And as an added bonus, it's really expensive to produce. Compilation is hard work. So again, steals time from your application. And again, we've got lots of compilation threads, to sit around in your address space and make it confusing to debug and all that kind of stuff. Also, VMs act like silos today. They're not aware of each other. So there's no choreography going on at the JVM level that says, JVM1 is busy garbage collecting and using all the cores. If I can defer the GC activity in JVM-B for a little bit and let that finish, that would be a great decision, right? Doesn't happen today. That's the other part of my job. But if we can improve the choreography that goes on within the JVM, there's an opportunity to get some of those pause times back under control, make things a lot more predictable in production environments. So what do we need to do to fix the cost of entry problem? First, we got to fix the state isolation problem. Tenant A being able to see tenant B. Second, we got to fix the resource hog problem. And the additional constraint that I get, because IBM, like probably a lot of you, we have a lot of software out there already, and we're not rewriting the whole thing. So I get to do that without making any application changes at all. So let's talk a little bit about data isolation and where some of the challenges come from. Typical pattern here that causes some pain for multi-tenant applications. You can see the web servlet annotation that's got some very convenient syntactic sugar for things like the servlet name and the URL patterns. That's great. It's, as a programmer, I do like this. It makes life easier. As an ops guy trying to deploy the code that we built, I like it less because suddenly the class files have configuration metadata embedded in them. And I either need to go and undo that with more configuration files, which is always exciting, or using tools like BCI to rewrite the code, which, again, ops guys don't tend to enjoy a lot because they add another element of unpredictability to the stack. So you could wean yourself off of these. Challenge number 2 is a little harder. Static variables. Within the heap, if I give an instance of an object out to a tenant, and each tenant has their own instance, those two computations can run off and not share any state, and basically complete happily, right? The problem occurs when you start introducing static variables into the world. So this is a bit of a contrived example. I've got a little locale settings class, and I've got some static finals that declare instances of those, one for Canada, one for the UK, and one for the USA. And because I sit in Ottawa, the default locale will be Canada, and that makes me happy. But now we've got a problem. So when I got a customer that is sitting in the UK or in the US, and they would prefer the locale to be different, what do we do? Right? So we've got some options, I guess. We could wrap the whole class in a class loader and load up one per tenant, which is kind of a lousy solution. Because again, got to go rewrite the code to do that kind of stuff, right? Get rid of the static variables, but again, we've broken the thou shalt not rewrite all your code rule. Or again, we could do some BCI to go and make every access to a static variable interact. And that actually works, I know, because we went and did it as a first cut. It tends to be a little bit error prone because there's some statics in the class libraries that you don't want to isolate. And one of the other challenges with BCI is when you get multiple BCI agents running at the same time, they don't always coexist very well. So as a across the board kind of solution, that's one that we weren't terribly happy with. So when you're stumped with a hard problem, you do the normal thing and go and read for a while. And I had the advantage of actually working on a pretty cool product back in the 90s, early 2000s called Visual H for Java. It was one of the first IDEs for Java. It was actually all built in Smalltalk, so it was one of the most ambitious Smalltalk projects I ever worked on. Had a very cool virtual machine that had both Smalltalk opcodes and Java opcodes and mixed language stacks, so really fun. However, for the guy trying to develop Java applications, what they saw was a really tiny footprint and blazing startup. And the reason they saw that is we shared all of the code and we kept the data separate. And I should also point out, Sun did similar work around the Java language with a project called Barcelona, sort of 2003 to 2006. So there's lots of good references to look back upon. They just need to be updated a little bit to work in today's Java environment. And I had a chuckle actually when I saw the hardware requirements. You need a massive 256 megabytes of RAM to run Visual H. And this thing could actually run tens of Java applications in that much space. So you had the full IDE, the full runtime, and probably 20 to 30 apps running reasonably well in 256 meg, which is a number, if I'm a cloud guy, that's pretty compelling, right? So how are we going to get there? I had to make one change. So the one change I'm going to force people to do is add a single argument to their JVM command lines. So this is a fairly major change. You probably don't want it by default. So enter -xmt for multi-tenant to your Java command lines that says, yes, I'd like to opt into multi-tenancy. What you see is your application behaves exactly as if you had a dedicated JVM, but in reality it runs side by side with other applications. And the reason we think this is cool is it's smaller, faster. Because everything's in an address space, we have an opportunity to do some of that choreography that I was talking about so that GC activity on tenant A doesn't interfere with tenant B. We've eliminated a lot of duplication. So we have one garbage collector, one JIT. The heap objects are all in the same heap. So I now have an opportunity to share them. Startup time. Because the VM is already up, pre-warmed, the JITs had a crack at a lot of the code that's important. The startup time is blazing. So how does this feel? I don't know if you can actually read the text. It says java-xmt-jar 1.jar. And this feels just like a regular Java launch would. What happens when the VM comes up is you actually don't run a full Java VM in that process. You run a little stub that goes off and finds our Java daemon. So the Java daemon is literally like any other daemon process. It hangs around. This is where all your shared state lives. And a large amount of the class library that's common run to run, we can scaffold up once, share between instances, and that's exactly what happens. So JavaD has all the expensive shared state. We create a new little box inside JavaD for your tenant and pass control back, and you have your own standard in, standard out, standard error streams, because you launched a separate process at the command line. You have a target for sending signals to, so it really does behave just like a regular Java application. The interesting part comes when you launch the second one. Right? And what we do is the same series of steps. We go looking for the Java daemon. Oh, hey, it's here this time. So I don't have to do any of the startup. All I have to do is inject a new tenant into it, and we're up and running. I've got some performance numbers later, but on startup we're seeing about 3x faster, which isn't too bad because from an elasticity standpoint, the best idle application is the one that's not running at all. And if you were just on the edge of being able to take the applications down, but the Java startup time is killing you, the 3 times faster startup may make the difference so that when your app is idle completely, you just shut it down, kill it, and use a multi-tenant daemon to get up and running fast. And you probably caught me in the lie that I hadn't actually fixed the data isolation problem yet. I just distracted you and described a shared container. So here's what we're actually going to do about the data isolation challenge. We're going to add a new annotation to the language. It's called @tenant-scope. It's in the com IBM tenant package, which is what the first red rectangle is showing us here. And what we need to do to tell the virtual machine that the default locale variable should be stored per tenant is to drop the tenant scope annotation in front of the variable. That's it. So at class file load time, the VM recognizes these things, sets a couple of bits, and we've added some path length to the get and put static paths so that it does the extra level of indirection for free. No BCI involved, none of that stuff. Naturally, JNI works as well. And the end result is that every tenant now has their own locale settings, default locale. Unfortunately, what I've just shown you is a code change, right? And a year ago when we were standing up doing this talk, we said it's going to be reasonable to have people go through and mark up their code with our lovely new annotation. And we promptly got told the answer was no. So this year, I have a different answer. This time, tenant scope markup gets added automatically as classes come in. So every static field gets it for free at load time. And this is okay because the JVM is doing bytecode verification anyway, right? We're already traipsing through all the bytecodes, having a look at the fields, making sure the types are compatible. So the extra little bit of work that we have to do really is in the noise. Are we leaving some sharing in the table? Absolutely. There's some variables that don't need to be isolated, but as a first cut, I'd say the extra little bit of sharing that we've lost is worth it for not having to make any application changes. And because I'm a sneaky VM guy, I actually snuck in some extra stuff as we were talking there. We've implemented a lot of this stuff in the class library up in Java beside, almost like a Java-lang class or Java-lang string. It's basically a primitive Java class that the VM has intimate knowledge of. So we think we can actually expose a lot of the tenant infrastructure for people that are trying to build, real tenant-aware applications. We use it to build something fully transparent like the XMT support, but we have a tenant class that knows about data isolation, knows about resource management. It's got API for both of those things. It has lookup so that when you're running on a thread, you can get to your current tenant really, really efficiently. You can get from an object to the tenant that owns it really efficiently. And it's a fairly thin API. So this is still in a fairly heavy state of flux. As we implement features like XMT, we notice rough edges. So we're evolving the API. And I think the timing here to do something out of the JCP and kind of the Java 9 timeframe is excellent because we found that quite often we find ourselves passing blocks of code to a tenant and say, hey, tenant, please run this piece of code. That would become a lot nicer syntactically with some of the language features like Lambda that are coming. So I think some of the work streams out there are starting to merge in ways that'll make life easier for your average programmer. So at this point, we're done, right? Yep, question? If we're using one VM, how about PermGen? J9 doesn't happen to have that problem, but yeah. And I think the hotspot guys are on the path to doing that as well. It's a good question, though, actually, because in all seriousness, I'm sure we've made design decisions that are tied in some way to the internals of J9, and if we're going to standardize this stuff for real, we got to have discussions with the other VM vendors. So. Yeah. So. Yep. Yep. Right. Yeah. So I guess the question was, Yep. If they're heap objects, then your objects get allocated in the tenant that you're running in. And I think I may have the slide that answers your question in like 2 slides. So if I haven't answered your question in 2 slides, stop me again, because VM guys are sneaky. So protecting the innocent, right? This basically just requires good walls between the tenants. And the closer your neighbors get to you, whether you're sharing a process between multiple apps today in a regular JVM or a multi-tenant JVM like I'm trying to build, the better a wall you can create, the more predictable things get. So the kind of controls that I've got today are CPU time, the amount of heap you're allowed to consume, the number of threads you're allowed to consume, how much file I/O you're allowed to do, so your read and write bandwidth, how much socket I/O you're allowed to do. And I'm sure there are going to be more of these as time goes on. But this has been enough to do some fairly interesting things. And actually one of the more interesting points that we run into is, even if I don't use any of the new fancy multi-tenant stuff, the tenant API is lightweight enough that if I'm curious about the behavior of a given piece of code, all I've got to do is create a tenant, say run this block of code inside the tenant, and then the resource management stuff can tell me how much heap it used and how much CPU it used. So it's, as you're developing, it's a nice tool to be able to understand the performance ramifications of the code that you're writing. A little more about ergonomics. Command line switches. I wish I didn't have to add switches, but this is a new concern. So for things like CPU throttling, we have ranges. We took the inspiration from this from the AIX WPAR stuff. So we can, in the first example, specify the minimum amount of CPU that we want to give to a new tenant, maximum amount of CPU it's allowed to consume. If I want to do just the maximum, I can drop the first number. If I want to do things like network I/O, I can do that. Existing options, though, we map for free. So people are used to saying, here's how much heap you're allowed to use. We might as well make it easy on people and just take those options, alias them to per-tenant things. And yeah, we're working on the MX beans so that you can see how much of each resource you're using. We've kind of got an open research question right now as to whether we should take over the default MBeans that you're used to using or grow a new set per tenant. So, there's arguments on both sides of the fence, and I don't have the answer for you today. Talk a little bit about putting the teeth into throttling. Here's the basic story, is there's an existing JSR out there for resource management. It's JSR 284. It gives us a good API to describe resources and how much of them you're able to use. And to avoid reinventing wheels, we just decided to underpin with a JSR 284 implementation. So tenants sit at the top of the stack. We've got a resource management layer in a really gross colored box here. This is inside the tenant APIs. JSR 284 sits underneath those, and then you'll see the resources that I mentioned before, like CPU and memory, etc. Inside our implementation of JSR 284, however, we have 2 choices for providing the teeth. One is the JVM does the enforcement. Choice number 2 is we ask the operating system to do the enforcement. So far we've done Linux C groups and AIX workload managers. I've got a performance chart, actually, next. It talks a little bit about that. So this is This is a graph of Fibonacci computation, a multi-threaded thing whose job it is to go and choose CPU. And we've cranked 2 tenants up in this case and given them a 30% and a 60% slice of the CPU, respectively. And then we went and measured how much they actually used. And the graph on the left shows what happens when we ask the operating system to do the CPU throttling. The graph on the right shows what happens when we do JVM sampling to control CPU usage. And you'll notice that we managed to get the lines in the right order, but there's still a heck of a lot of jitter on the JVM supplied version. And the table at the top just shows you the running time of the two. They're about equivalent cost-wise. So I certainly like the picture on the left a whole lot better. And the operating systems are good at this. However, the OS workload managers really do not like working at the level of a bunch of threads within a process. They much prefer to deal with processes. So we have some work to do with the OS guys if we want to go with the answer on the left-hand side. If we can clean up the jitter a little bit, we have a nice portable answer on the right-hand side already. But at the end of the day, we can already control resource consumption between tenant A and tenant B in a way that you can't do with today's JVM. It was 3 slides. Here, hopefully, is the answer to your heap question. So we've had new region-based garbage collection technology in the IBM's JDK for a while. It was designed for large, big 64-bit heaps. And the way it works is by subdividing the heap into a bunch of fixed-size regions, and we do that so that you can do more work in parallel and don't have to traipse all over memory in order to collect. So again, wearing my cloud hat, I looked at this and said, that's almost a perfect fit for what I'm trying to do with tenants. So if I can say, hey, tenant, here are a number of GC regions, enough to satisfy your minimum allocation, and you can come to me and ask for a new region, but I may say no and you can't get it. That gives me a way of capping how much heap somebody's allowed to use. And we've tweaked the allocators so that when you're running code in a given tenant, so the way this picture works is there's a tenant A, which is blue, tenant B, which is green. They each have some number of garbage collection regions. When code is running inside tenant 1, it will be allocated into a blue region. When code is running in tenant 2, it'll be allocated into a green region. And the two sets of objects are never allowed to mix. Right? So objects are fully segregated. Yep. Yep. And one of the nasties here is we have a fixed number of regions. It's just an implementation detail right now. So that I can't hand you out less than a full region today. So that impacts the minimum amount of heap I can hand to a tenant. But so far it seems like a pretty good model. And actually it's going to be important when it comes time to deal with misbehavior, because there's circumstances where you have to take out a tenant. It's being badly behaved, you want to go and shoot that thing. And one of the big problems with thread stop is the VM is capable of going and unlocking monitors on a stack, but as soon as you've gone and broken monitors, you've basically corrupted all the objects they're talking about. However, the advantage we've got here is we know all the objects are segregated, and if the tenant's dying anyway, you've minimized the splash damage, right? It's going to occur within the JVM when you do things like kill. The another nice feature about segregated objects is it allows you to do things like mapping quickly from an object back to its owning tenant, right? It's just an address compare. Also, GC read and write barriers give us an opportunity to catch people that are trying to point between tenants at the source. So, particularly for class library implementers that are working on that shared piece, there are situations where you can wind up with a green object pointing at a blue object, and we want to disallow that. Right now, it runs across all of them, and the region-based GC was always selecting the regions that it wanted to collect based on highest chance of reward, basically. It's got a heuristic built into it that says this is a fruitful region to collect. I'm going to pay attention to that one and leave these other ones that are less hot on disk. So we're just tilting that existing decision to say, look, please pay attention to the tenants that are currently hot. GC tuning is one of the areas where we've got a lot of work to do in the next year. Yep. Okay, I'll have to dig that up and I'll fix the slides that are uploaded. I was trying to get to the white paper on BalanceGC, so you should probably be able to do like a J9 BalanceGC and find the white paper. Yep. Right. So the question is, what does it look like from the operating system perspective? And the answer is you have one instance of Java D, which is the shared daemon, and one instance of Java for every tenant that's attached. So remember, we were typing java-xmt. That process is still there, still kicks around. It just happens to be really, really small because all the heavy lift is happening over in Java D. And that's the reason that we're doing beans, so that you can snoop around at what's going on inside the Java D side of the world. Oh, questions?
So basically for an application like Tomcat or like how does this apply? And then the multi-tenant basically is the back. And like multiple clients of opinions, they might be
Yep. Okay. So the question was, how does this apply to something like Tomcat or Jetty or a typical application server? And that may have actually been the segue I was looking for to my next slide. We'll skip this. How dense can we go? Right, here's what we're actually working on today. So IBM's been doing a lightweight server. It's the WebSphere Liberty profile. You know, it's similar to a Tomcat or a Jetty or something. It's OSGI based, but it's a small server. What we're doing now is running multiple Liberty instances inside one process. So one Java D, lots of Liberty instances, so lots of Tomcats running on one process. You separate the configuration information, so you know they all have their own port. You got to be a little careful about log directories to make sure they're not standing on each other. But that's the same problem you would have if you ran multiple Tomcats on one operating system instance today, right? What are we doing about safety? Stronger walls between tenants is our current to-do. We've got the read and write barriers in, and we're now working on robust finalization and cleaning up some of those inter-tenant references that we don't want happening. We're looking at a different take on quota enforcement, actually. So one of the way JSR 284 would like you to deal with overrunning your quota is to throw an exception, which isn't really the friendliest thing that you could do to a thread. You know, you might be better off stalling it for a period of time and then giving it another chance to run. So we're looking at different ways to deal with the overrun cases that are maybe a little more friendly. A lot of our focus right now is performance, so figuring out how to measure density and quantifying what the throughput tax is, because again, we've added path length to every get and put static, right? And those things are used heavily in logging frameworks, stuff like that. So we're currently doing the JIT support, and I should have some throughput numbers for you shortly. And then simplifying configuration for things like those command lines about how much of a given resource are you allowed to use. And you know, I think we're at the point where big applications are running. We're at the point where we really need feedback, right? So we're, as part of the Java 8 beta program, going to put some drivers out on developer work so people can pick this stuff up and, you know, use it in anger, see how it works in their environment. I have thick skin, so if you don't like what you see, please tell me, and we can try to fix some of that stuff up. And if that shows promise, I think doing something through the JCP makes a lot of sense. So, performance data, that's the next thing. How we measure this is actually one of the more fun little hacks we've done recently. From our mainframe experience, we know that you can actually overcommit on CPU in a ratio of about 40 to 1. So a 1/40th slice of a CPU, you can actually get some useful work done on. Memory is the tightest resource. So the way we measure this stuff is a tiny little VirtualBox guest running Linux. 1 core, 1 gig of RAM. Big advantage here is it's really easy to control, really reproducible because you can reboot it, get right back to the same state every time. And then what we do to make the math easy is we just add applications until that system starts to swap. As soon as you go into swap, we say, hey, you're full, more applications is better, and your per tenant cost is how much RAM is in the box divided by the number of tenants you're able to bring up. So everybody shares equally in the operating system bills, and that takes care of the Java versus Java-D accounting and all that sort of junk. So far, we're seeing about 3x faster startup, which I think I said earlier, and up to about 5x the density. So 5 times as many applications on the same box, which is pretty compelling. Now, of course, I picked the best number I've got, and that's for simple apps. Stuff that's mostly using base libraries. As soon as you get into user-defined class loaders, we've already instrumented the JVM, the Bootstrap and EXT and app loaders. They know about tenants. User-written class loaders, like the ones that are in OSGI, don't. So, there's sharing we're leaving on the table, but for a 1.0, the numbers are looking pretty good. We're still working the JIT support. I don't have a good throughput numbers for you yet, but we're already seeing numbers like 4 megabytes per tenant. The thing that killed us in this particular, I should explain. So, performance chart on the bottom. More tenants is better, so longer bars are better. Untuned, I got 19. This little application started. I cranked the heap sizes way down. I managed to get 51 packed onto the box, and our multi-tenant stuff ran out of gas at 250. And I think we have a path to make that number about a 500 pretty easily by lifting some internal region count limitations. So, for a certain class of application, the numbers look pretty compelling. In case I made this seem easy, there are details. As soon as you start to share heap objects, some of those things are special, particularly Javalang classes and Javalang string instances. They have monitors, and you don't want tenant A interfering with tenant B from a synchronization standpoint. So we think we have a solution there by allocating monitors when they're contended. Finalization, again, that's a shared service. There are lots of shared services within the JVM, but whenever you've got one, you're duty-bound to protect the shared service. In this case, that means fast mapping from object to its owning tenant, and the ability for the finalizer to be able to recover from a malicious denial of finalization attack. These tests are actually the most fun to write. You can sit down and write misbehaved Java code for a week or two at a time. It's awesome. I'll do questions at the end, actually. Support for JNI natives. This one's hard. So you've only got one process. If you have multiple load library calls and they're talking about different libraries, the operating system's not going to let you haul in 2 different versions of libfoo.so. So the solution there is to run the JNI natives back in the launcher process. Remember, every tenant has its own dedicated launcher process. That's the place we can send signals. It's also the place where it makes sense to run JNI code. The problem here is path length and some latency because the JNI path is pretty performance critical. But folks like Azul already do stuff like this. We have similar technology in J9. Killing misbehaved tenants is hard. Again, we talked earlier about, as you unwind stacks and break monitors, you're effectively tossing the internal state of every object that you do that to. But again, because we've segregated all the objects, we can make that as safe as it can be. Class loaders we talked about a little bit. Barcelona actually had some really good thinking in this area, and Eclipse has got a CDS adapter, so this is a piece of technology that knows how to play nice with J9's class sharing. So the thinking here is that once we've made the decision that it's safe to share the ROM portions of the class, there's a little bit of extra work required to share the RAM portion as well. We think that that'll save us about an additional 25%, but it's going to be a 2.0 kind of an activity. And then postmortem debugging is really fun because if anything goes wrong in JavaD, all the information for all the tenants is in there, and you have choices about either filtering what people are allowed to see as you're generating the artifacts or trying to cleanse the cores after the fact. So that's a fairly big open question for us. So thus far, focus has been 0 application changes. The primitives that we're building, we think are going to be generally useful. I can make it fully transparent, but the same tools I use to build that, we want to expose to people building regular multi-tenant applications as proper API. A lot of this stuff is already standardized, so resource management's out there, isolates are out there, tenant scope fields we'd like to put out there, and we're already seeing some evolution in the Java ecosystem, right? So we've got EE8, SE9 with multi-tenancy on the slides. Maybe this is part of the solution. Eclipse Link you can pick up today. It's got some sort of alpha multi-tenant support, and our beta program should be March, April next year. It's probably your first chance to try this. And in case you thought you got off easy, what should you be doing to your code today? Performance tuning, so you're a better neighbor, right? So when you're idle, don't choose cycles. That'll just make you a better neighbor in any case. And also prepare for overcommit. So remember we talked about orchestration. Knowing the busy and idle cycles of your applications can help you pack them denser today by aligning the busy and the idle bits, get more out of your hardware. So hopefully you believe at least some of what I've said. I think simplifying and removing some pieces of the software stack that are arguably extraneous, maybe a bit of an extreme view, can make things simpler, cheaper to run, and a whole lot more dense than we can get today. And yeah, we're going to trade some isolation, but we're going to get the footprint and agility back out of it. I think this is my last one. Yeah, so we can do single-digit megabytes, hard work for me, ideally easy work for you guys. And when that beta comes out, the thing that you can do most to help us is just give us feedback, let us know how we're doing. Yeah, actually, so the question was, do we have plans to contribute any of this stuff back to OpenJDK? And the answer is yeah, definitely. In order to do the resource management pieces, we've been through most of the native layers where the class library touches the operating system in order to insert throttling. And I think that's a series of changes that are useful no matter what. Right now we're benching them to make sure we haven't regressed performance in any measurable way. Once we're through that, then filtering them back in through OpenJDK makes a heck of a lot of sense. Tenant scope stuff, again, unintentionally, I'm not trying to be evil, but I bet you we've baked in a J9ism or two to the way the API is spec'd. So I think when we converge on an API we're really happy with, having a discussion with the hotspot guys makes a lot of sense. Question? Sure.
Yeah, one of the ways that we segregate our applications is they run under different IPs, so they can't touch each other's files.
Yep.
File security. How would, in a multi-tenant application, would you allow the tenants give these multiple application IPs to the tenant?
Right. So the question was, today we run our applications under different user IDs, and how is that going to work in a multi-tenant world? And the answer is that we actually create one instance of JavaD per user, and that enables the JavaD process to reach to all the places that user is allowed to reach to. So it's not like there's one Java daemon per machine, there's one Java daemon per user. Does that make sense? I'll draw the picture for you after. Question? Right. So the question was, what I've shown today, does every tenant have to spawn its own Java process? And the answer is yes. That it's a simplification basically to allow you to type java-xmt on the command line. You know, that process you created when you typed that, you know, we're going to make it as small as we can, but you do get a new process. It actually happens to be really handy because a lot of our service folks, you know, have tools that are built around send the process that you're interested in a signal and have it produce core files and diagnostics and that kind of stuff. So having a first-class operating system thing that you can send that signal to actually is pretty important. Right. 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 Yeah, and I guess I'm trying to figure out how to restate the question. I guess it was reality says we're actually going to have multiple instances of an application, and how are we going to deal with that for multi-tenancy? And I guess my answer is sort of twofold. We've been trying to make standing up ensembles of infrastructure easier through things like, if you look at the Pure App talks, they talk about virtual application patterns where you describe things like, you know, I want a load balancer on the front, and by default I want 3 instances behind it, and here's how you're allowed to scale that thing up and down. I think that's part of the machinery that we're going to want to use to try to put the scaling decisions into the middleware. And the nice part about multi-tenancy is that, you know, you can probably bring up more instances because the individual ones are cheaper, right? They're not costing you gigabytes, they're costing you single-digit megabytes, hopefully. But I don't think the load balancers and stuff of the world are going away. Question? Right. So the question was, how do you solve the I/O conflicts? And my answer is, you know, that's not one of the things that we're trying to fix. So if you have a problem running multiple regular JVMs in a single operating system, you're still going to have the same problem with the multi-tenant version. So typically that means that you need to configure your app servers and, you know, sort of the configuration metadata so that they're all writing into their own homes, basically.
This may be an extension to a previous question.
Yep.
How, if there's a cluster, you know, I want to run multiple clusters of my multiple servers in a cluster.
Yep.
So will there be multiple Java Ds, and then each Java D has X number of Javas running associated with it, or?
Yep. So I guess the question was, if I was going to run in a cluster, what does the layout of Java and Java Ds look like? So the cardinality is basically one Java instance per tenant, and you can configure how many Java Ds you're allowed to put into it. I think, again, we're going to want to teach the deployment machinery what the policy is. You know, we're going to have hard limits of probably, you know, 200, 300 tenants per process, which actually is more than most people are likely willing to put into a given basket. But yeah, it's basically that, you know, one Java to one tenant. That's today's answer. Ooh, question all the way at the back. Right. So the question was, if I'm using that sort of user isolation and running each Java as a different user, and I'm only running one of them, will my multi-tenancy buy me anything? And the answer is, if you've only got one, no, it's not the right tool for that job. The sweet spot for this stuff is really where you have lots of copies of basically the same application. right? And you need them to start fast. So that it's actually, for a lot of batch workloads, it's almost an ideal fit where, you know, you're going to wake up and do some piece of Java work and you want that startup to happen as fast as you can, and it's going to be the same computation time after time. We see a lot of that in the mainframe space, actually. Question? Cool. Right. Yeah. So the question is, are you targeting larger hardware? And the answer is, yeah, absolutely. The current implementation, for example, is 64-bit only. Because you have that one big shared region, it really does cater to large heaps. And mm-hmm. Yep. Yeah. So the question was, now that you're co-located, have you thought about shorter path links for VM to VM communication? And the answer is, yeah, we're really, really interested in that stuff. We see a lot of it today. You know, we're looking at things like RDMA and exposing verb APIs directly up in the Java layer so that, you know, you can minimize the amount of copying going on. It hasn't been the killer issue for the multi-tenancy stuff yet. You know, you can probably see that we're just trying to get this stuff up and bootstrapped. I think there's huge opportunities when you're all on the same heap, you know, that you should be able to take that path length way, way down. All right. And I'm happy to stick around, so I'll stay up here talking as long as you want me to. So what's the amount of heap we've tested? We've run this up to about 28 gigs so far. Yep, so the question is, I thought the isolate API was dead, and the answer is it's been quiet for a long time. Like JSR 284, you know, that JSR has been around for quite a while. It might have been an idea that was before its time, right? Because you look at some of the cloud concerns and, you know, small containers and being able to throttle resources are pretty fashionable right now. So whether we can just reach back and, you know, take what's there, you know, it's sufficient. Do we want to shine it up a little bit for, you know, the next generation of multi-tenancy support? Yeah, probably. Yep. So the question was, if I had 3 different applications, is it possible for them to live within the same Java daemon? And the answer is yes. If you would run them with the same JRE on disk, then, you know, you're free to share the same Java D as well. So, you know, the things that are in the ext directory would be visible to all of them, but if that's a restriction you're happy to live with, then... Right.
When I was on a per-application basis, I had XMS, X,
right.
X, control the maximum of.
Yep.
All this, the Java D grows all the other VMs.
Right. So the question was, you told me that you stole the XMS and XMX settings to be per-tenant things. What are you going to do about the Java D daemon as a whole? And the answer is we've actually got a config file of options that get used by JavaD on startup. It's a regular Java invocation behind the scenes, so any option that you know and love on the standard JVM, you can feed into the daemon, and that's how you could cap and set initial sizes, for example. Yep. Yeah. So you can define the resource envelope that you want the JavaD to run in as well. Right. So the question is, is all the memory allocated in JavaD, I guess, aggressively? And the answer is no. We give you a minimum reservation. We allow you to grow up to your maximum, but it's sort of like overcommit. We basically let the system sort it out up to the limit that JavaD is allowed to hold on to. So we've said an individual tenant, can't get bigger than this. The JavaD can't get bigger than that. But if you put more work into it than the thing can hold, you can still blow it up. Yeah. Yep. Right. Yeah, so the question was, do you do CPU tracking for chargeback? And yeah. So the way that we've got that working today is that you can check in on a tenant to see how it's running, as it's running, and that's what we want the beans for. And at the end of a run, you've got sort of aggregate usage stats for what that tenant's done. And I hinted at it earlier, but one of the things that we're actually using it for is, you can create a tenant and you can say, please run this block of code inside the tenant, and the tenant dies at the last line of your little program, but it can also give you resource data there and then. Right? So it's a very cheap way of saying, please help me understand what's going on resource-wise in this block of code. Oh, one more. So the question is, do we optimize JITted code differently for different tenants? And the current answer is no. We're just trying to get the JIT support going at this point. But it's an interesting question. Yeah, I think this is the beginning of multi-years of work. So, right. Question? Yes, the question is, did you compare and contrast yourself with Waratech, which is the other company doing multi-tenant stuff? And the answer is no. I didn't even know about them until I saw they were a bronze sponsor, but they're on my list to go chat with. Cool. I think I've exhausted the supply of questions. So thank you for coming. It's been fun to show and tell, and my contact info is on the slides. Feel free to reach us if you've got questions, comments, anything. Thanks much.